going to be looking at some other situations today. This is just talking about really the scenario that we were looking at last week. So when you have the graph of a continuous positive function on an interval and we rotate it around the x-axis, what was the shape of the cross-section we saw on almost every problem? Right. And we found out that we know the area of a circle is pi r squared. And what were we using for the radius on those? Right, our f of x. Okay, and that worked out on all but I think maybe one problem that we did last week. There was one that was like semicircular, and we had to divide that by 2. But the rest of them had a circular cross-section. On all of these problems, we were using what's essentially called the disk method, which was what we did on every single problem, so you don't have to memorize this as something new. But it's when you have those circular cross-sections, the radius was just the function, and so it's really just pi times the function squared. And we're integrating from A to B, left to right. Now we did see sometimes we had to do from top to bottom when we had that function where the x value was changing. Then we may have to switch this and do it in terms of y sometimes. Let's look at this problem. So I want to find the volume of the solid formed when the region enclosed by the curves y equals x and y equals x squared is rotated around the x-axis. Okay, this is already different than Friday because I've given you 2 different curves here. Friday we were just taking a single curve and rotating it around the x-axis. So if we draw a picture, okay, y equals x is just our line. Y equals x squared is a parabola. Okay, so really the relevant part, the region enclosed by these 2 is right here, isn't it? So what we are doing is spinning that little piece around the x-axis. So we're going to take that, and as we spin it around, you're going to get like a cone. But how is this different than the cones we were getting Friday? Yeah, the ones we were doing Friday were more solids. So you got, this solid piece. This is like a funnel. You have the edges, but it's empty in the middle. Okay, so this is going to be a little bit different than what we were doing before. We know that we have to integrate our area, right, to get the volume. It's the antiderivative of area. So the area of this, we know that's pi times our radius squared. So the radius of this, I want just the solid part. What are you going to have to do? If you just had the line, what would your radius be? X. If we just had the parabola, what would your radius be? X squared. So what do I need to do with those things? Am I going to add them, subtract them, multiply them? Subtract. Just like you want the area between 2 curves, we did the top curve minus the bottom curve. We're integrating the area, so we need the top curve minus the bottom curve. Okay, so when we are talking about the radius here, we're going to have to do the top radius minus the bottom radius. So it's pi times the radius squared. So the top one was x, and you would square that, minus the bottom one is x squared, and we square that. So we are squaring these pieces individually. Think of it like if you had a donut, Okay, and I wanted you to find the area of your donut. You would find the area of the big circle, you would find the area of the small circle, and you would subtract those two, right? That's exactly what we're going to do here. We're essentially doing the volume of the whole thing. We're going to subtract off the volume of the inside part, because that's what doesn't exist. Okay, so we are going to integrate from where to where. I need to find out when these curves are equal, don't I? So when does x equal x squared? So if you subtract over your x, they're equal at 0. So we are going to integrate from 0 to 1. The pi is just a coefficient, so if you're more comfortable, you can pull that out in front of your integral, if you would like. And so then we just need to do x squared minus x to the 4th dx. So the antiderivative of x squared is 1/3 x cubed. Antiderivative of x to the 4th is 1/5 x to the 5th, from 0 to 1. And so we should get an overall area of 2 pi over 15 here. Or not area, volume. 2 pi over 15. So this scenario is different than the disk method, which is what we were doing before, because this involves two functions being revolved around the axis at the same time. This is what's called the washer method, because you have the center cut out, so it's just like a washer. And so what you do is the outside minus the inside. So that's our washer method. Okay, we're going to do a couple more, and then you guys are going to have some time to work on problems. Okay, now we're going to throw a real wrench in it. So I want the volume of the solid from the last example, but now instead of turning it around the x-axis, I'm going to rotate it around y equals 2. So, I really feel like Lauren should be up here drawing this with me. We know those things met at 0 and 1, right? So here was my line, here's our parabola. That's the solid we're looking at. Where's the line y equals 2? What is that? What kind of line is it? Horizontal line at 2. Okay, so if I'm going to rotate around that line, think of it as if we just reflected it across first. Then, this point would go up here. But I'm spinning these things. So it's kind of like a Christmas tree stand. Okay, but we just spun it around a different line this time. Okay, so this is all shaded region here. But it's hollow in the middle. Now the real trick, because it's not centered around the x-axis, our radius is not just our function this time. We're going to have to think about it a little more. So from the line where we are centered around, which one is the outside function? my green line out. The outside function is your parabola, right? Okay, so let's just talk about that for a second. So the outside radius. We need an equation for it. We know x squared gives us this y value, but I need it to be measured from 2. I need the distance from 2 to that point. So what would you have to do?
X plus 2.
Close.
Would you multiply by 2? Since it's...
That wouldn't necessarily. It would only work in some places. You need to do 2 minus x squared, because we essentially want to leave off this bottom. So the outside radius is 2 minus x squared. The inside radius it's also centered at 2, so it's 2 minus. The inside one only has to go to x, so the inside radius is 2 minus x. So to get the volume, we're integrating. We have the same intersection points. We're going to go from 0 to 1. You can pull out the pi if you want. We're integrating area. Pi r squared. So you have to do the outside squared minus the inside squared. Have I lost anybody? So I would probably multiply all this out before I try to integrate. I think that would help a lot. So that would give me 4 minus 2x squared plus x to the 2 minus 4x squared. So if we simplify this, what happens? 4x, and the 4's drop out. So now we can actually integrate. So x to the 4th would be 1/5 x to the 5th. 5x squared would go to 5/3 x cubed. 4x would go to 2x squared. do another one with this same scenario, because it's so much fun rotating it around different lines. So, same solid. This time I'm going to rotate around x equals -1. Start with that. X equals -1 is a vertical line. So if I rotate this around, okay, we're just getting a fold here as we spin this around. Okay, so it's hollow in the middle, so we know we're going to have to subtract off. Usually, we go left to right. What's the problem with this?
Right, just change.
Yeah. Your left and right values change depending on where you're at the bowl. So we have to switch gears totally. I can't go left to right on this one, so how am I going to do it?
Y.
We're going to do it in terms of y. We'll go bottom to top, and we're going to use y for our variable. Okay. What are the y values where these things are equal? Do we know those?
0 and 1.
It's still 0 and 1. You know our equations for y equals x and y equals x squared. We know those are equal when x is 0, which if you plug in 0, you get out 0. And when x is 1, if you plug a 1 in for x, you get out a 1. So my limits are still from 0 to 1, but this will be in terms of y. Okay, so let's talk about the radius. So outside. We agree that this is circular, right? So the outside radius, if you are starting at -1 and going out, the outside one is the parabola, the x squared. I would have to solve this so it was in terms of y though. So that means okay. Now radius has to be positive, correct? So could I say like -1 minus radical y for my radius? No, because that would give me a negative value. Radius is a distance, so it's positive. So think about it. We know from the x-axis, from the y-axis over, this distance is radical y. How far is it from the y-axis to my green line?
1.
1. So my entire radius would be
1 plus
1 plus radical y. The inside radius. Okay, we can think of it the same way. That's going to be the line, y equals x. So from the y-axis over, it would be a distance of x. To get from here to my line, it would be 1. So my entire radius would be 1 plus, but instead of x, we have to call it y. Okay. So we have to integrate the areas. Every circle is pi r squared. So you could set it up as, pi times the first one squared minus pi times the second one squared. I've just been pulling my pi out in front, so it's one less thing to worry about as we work through it. So I need to do the outside squared minus the inside squared. we start multiplying everything out. It gives me 1 plus 2 radical y plus y plus 1 plus 2y plus y squared. So if I combine like terms here, I end up with a negative y squared, a negative y, positive 2 radical y. So integrate. Negative y squared would go to negative 1/3 y cubed. Negative y would be negative 1/2 y squared. 2 radical y, that's like 2y to the 1/2. You add 1 to the power, multiply by the reciprocal, that would give us 4/3.